Thank you very much for the kind introduction. It's an honor here to be among so many distinguished colleagues and talented students, and to be immersed in almost a full day of great discussions, and now have an opportunity to say a few things to you. So this is the second time this year that I drop in at LIDS. The first time it was for the student conference. Maybe I should see if I can apply for a Premier 1K status with LIDS, if there is such a thing. This talk will not be entirely different from the one I gave in February, but it will be a sort of a prequel. And it's a prequel in the following sense. The Control System Society has the so-called Control System Society Week, which contains the Control History Forum, and it's chaired by Professor Alberto Isidori, who asked me to prepare a talk on the history of PDE backstepping for this year's Control History Forum, which was in October. I felt that that was a topic that might be worth presenting here. Since history really doesn't make for necessarily an exciting topic, to make it also future-facing, I'm going to integrate at the end some of the elements of what was partly seen in February and what I had prepared for the Bode lecture a year ago. I have to say that the content of a history lecture is necessarily specialist-oriented, and I've tested this talk once at a plenary given at the Brazilian Control Conference about a month ago. And one piece of honest feedback that was given to me by the person who founded the Brazilian Control Association 50 years ago, so this is a gentleman in his late 80s, was, I understood nothing, but I could tell it was captivating. So my objectives here are modest in terms of the complete comprehension of what I have assembled, but I've worked very hard for it to be coherent and reflective of how the ideas actually developed. So the talk will be two for the price of one feature, three quarters history, 1/4 future facing. And let me be clear that this was originally put together to be a history talk. In other words, while it would be nice to give a tutorial or a survey, this is neither. It's an exposition of the historical progression of certain ideas. It's for the most part chronological, even though that's not necessarily pedagogically ideal always. It's definitely not comprehensive. I put the emphasis on the starts of certain subtopics. And since it's a historical account, the attribution is important. I was trying to give specific credit where that was relevant. You will see that a big part of this is concentrated in a certain team and group of mostly my associates, but it was over the last 10 years that this started to quite rapidly expand, and I'm very pleased by it. The future part will be a talk on how machine learning has found its role, or how I have found a way to prevent drifting into total irrelevance in the age of machine learning, and connect this broad and rigorous theory with methods of machine learning. So let me start with one slide on what existed in PDE control before the start of the so-called PDE backstepping. So for about 3 to 4 decades, the efforts in PDE control were focused on replicating the existing methods. So LQ, with operator Riccati equations rather than matrix Riccati equations, pole placement. There were efforts in extending H infinity, a few of those. And just to give a few references, these three, of which I note here that one of them was co-authored by Professor Sanjay Mitter, whom we all, I think, deeply miss in our field. But all these efforts were focused on extending linear methods to the infinite dimension. It is hard to imagine, looking at this literature, how it would extend to nonlinear PDEs, or how it would be turned adaptive in the way this was done for certain linear and nonlinear PDEs. So the root of the PDE backstepping actually is in feedback linearization, in the sense that in feedback linearization you have a change of variables and feedback. In PDE backstepping you have the same thing. So just a reminder of feedback linearization. There is a system affine in control with an output. You introduce a change of variables with these lead derivatives, and at the end you end up with a chain of integrators where in the last equation you have the control appearing, and with that control you can impose, if you wish, a linear closed loop structure and assign the behavior any way you like. Now, the limitations of this approach were immediately recognized, and people asked, what about uncertainties? What are you going to do if you have disturbances, or if you have a parametric uncertainty that is really, really large that you cannot account for it with a single controller? And this question, the extension of feedback linearization to these uncertain systems, occupied intensely about half a decade, the first half of the 1990s, and resulted in adaptive and robust solutions to stabilization or disturbance attenuation in nonlinear systems. So, as one of the participants in this development, when I was done with that, I was looking at what to do next, and interestingly, there were certain applications and activities and consulting opportunities in the aerospace and jet engine industry, and I realized how narrowly I had been working up to that point, how broad a space of dynamical systems is when you step away from ODEs and look into PDEs. So the first thought was the following. So this is a parabolic partial differential equation where the space is x, lambda is a destabilizing reaction term, and you can discretize it in space only. You keep the derivative in time, and this spatial discretization reveals that there is a chain of integrators here. You see ui dot equals ui plus 1. And you realize, oh, this is kind of like feedback linearization. So what this calls for is going all the way into the Brunowski form. The problem is that the transformation into the Brunowski form involves a matrix which, when the discretization step, the spatial discretization step is taken to 0, because you need to do that if lambda, if the instability gets larger and larger, that this matrix grows unbounded. So this is ill-posed. Feedback linearization taken literally is ill-posed for PDEs. So I realized you need to preserve the structure. There is a differential operator there, this Laplacian, that needs to stay. You can transform this, you can eliminate the reaction which destabilizes the system, but you need to keep the diffusion. So I did that. I messed only with the destabilizing term lambda, but I kept the diffusion. I replaced the destabilizing reaction with the stabilizing one. And here's what happens there. You obtain a gain which depends on the spatial coordinate x. So this gain k is a function of space. And as you take h towards 0, you observe a divergence. This is not a blow up, but you observe a divergence of the gain into a two-valued map. This is definitely not good. What this seems to be is something that should be converging to a mean of this two-valued map, but you don't get it through the discretization. So this is a second message, that doing PDE control, where the first step is the so-called lumping, in other words, the model reduction into an OD, is a dangerous business. We did prove stability with all of this, with these discontinuous games, with convergence in the weak sense. It's a nice exercise in math, but that's not what an engineer would want to see. So early lumping is a bad idea. You want to design a controller for a PDE and then discretize the controller in space rather than the other way around. So let me now turn the attention to a slightly more general class of PDEs. So this is now diffusion, reaction, advection system with a non-local term, and this is inspired by Navier-Stokes and certain other systems in flexible structures and in other domains. So here's how one goes about developing a continuum version of this transformation. One introduces a transformation that contains an integral in space of the state up to the current position in space x. If you think of this x as a time-like variable, you can regard this almost like some kind of a generalization of a convolution in space rather than in time. So it's not a totally foreign, weird object. If you look at this discretized in space, you see that this transformation of U is essentially the identity minus a lower triangular matrix, an invertible matrix by definition. So the transformation of this system is into something desirable, and the simplest desirable pedagogical choice would be the heat equation, the simplest of all the parabolic equations, which happens to be exponentially stable. So far, what I present here is a wish list of how one would want to organize a design. But is that possible? What kind of a kernel, K, would it take in this transformation to obtain a transformation into the heat equation? The answer to that is that this kernel equation needs to satisfy a certain PDE in space. I'm leaving out the boundary conditions. The domain is not a rectangular domain. It's a somewhat unconventional PDE, which I'm thrilled to say. It's a special, well-recognized class of PDEs called the Gursa form PDEs, and I have not seen a single physical system for which Gursa developed this PDE more than 100 years ago. It appears for the first time in the context of control engineering. So this is the equation that the user needs to solve offline before applying a controller to stabilize this PDE. Now, the first question that needs to be answered is a mathematical question. Is such a PDE well posed, and how would you solve it? And the answer to both questions is the following. Because of the Gursa structure, because of the triangular domain of this PDE can be easily converted from a PDE into an integral equation, doubly integral, I point out, where G and K are equivalent. There's just a change of the spatial variables x, y into C, eta. I don't need to bother you with this. This is beyond elementary. So this and this is equivalent. And this second object is an object that can be treated with successive approximations. You start with an initial function for G equals 0, then you keep substituting the resulting double integrations. And as you keep doing these double integrations on the initial function, which is given by the reaction term, you study the convergence of the resulting series. You establish this convergence, and this gives you the answers to both the well-posedness and one way to compute these solutions. Now, what was really thrilling was that for a constant reaction term, my student Andres Mishaev was able to produce an explicit solution to this PDE, which is this elegant but not trivial form. It involves Bessel functions, but not of x or y, but of the square root of the difference of the squares of x and y. Something, again, idiosyncratic enough to excite you as something that's never appeared in physics appearing in the domain of control systems. Now, the original objective for developing backstepping was that with existing methods, you could not even start dealing with nonlinear PDEs, and perhaps with PD backstepping, you could. So how do you extend these transformations and designs to nonlinear PDEs? So I give here a nonlinear PDEs in F, in which capital F could be a function, or it could be a nonlinear operator. And I postulate a transformation which now, instead of a Volterra integral, single integral, has this infinite sum of nested integrals with increasing, with products of u at different positions in space, Cj. And this is step one in developing a very comprehensive theory for nonlinear backstepping control of nonlinear PDEs. The target equation, again, there's no reason to take something super complicated. One can, like in feedback linearization, go for a familiar, desirable, linear closed-loop system, and one such system is the heat equation. What does it take to produce a controller? It takes finding the solutions for these kernel functions. These kernel functions now satisfy not one, but the whole sequence, an infinite sequence of PDEs on domains that grow from 1, 2, 3 up to an unlimited dimension of the domains. And all of this can be bounded, can be summed up, can be proved convergent, and can be implemented. So one slide on that. I'm going to leave it at that. So what are the possible applications? I have to say that for me, the driving application that at that earliest stage of the development of this was one that displays probably a bit of vanity, and that was the Navier-Stokes. Is there a more feared and more respected PDE out there than Navier-Stokes? So I thought, okay, this is the one to drive the development of the theory and to apply the theory to, and we worked on that, on the conversion of this system of nonlinear PDEs into a set of 3 heat equations with the convection retained, only eliminating the unstable parts, or specifically the unstable wave numbers in particular geometry. And I'll leave it at that, because Navier-Stokes was just one of the things along the way. I can show this slide. So this was the parabolic case, and up to that point, nothing hyperbolic was done. And turning the attention to the hyperbolic case, you want to look at hyperbolic equations that happen to be open-loop unstable. If you introduce this kind of a non-local operator into this system, and it's reflective of several applications in various wave systems, this is open-loop unstable. With a backstepping transformation of the kind that I showed before with the first order, with a Volterra integral operator of the second kind, one can transform this equation into the transport PDE. Now, for the electrical engineers like myself, what is this? What is a transport PDE? It's just a delay line. That's all it is. A delay line in which there is an initial condition, but you're putting nothing from time 0 onward. So this is not only an exponentially stable system, but a finite time stable system that settles in 1 unit of time. So it's a nice type of stability to achieve and possible to achieve, and I'll skip the details. I'm skipping the details because the interesting hyperbolic systems rarely appear as one hyperbolic PDE. Typically, they appear as systems of coupled hyperbolic PDEs. I will show you some physical examples, but let me show you just a general form of 2 coupled counter-convecting. I emphasize this sign difference in the convection term. 2 counter-convecting coupled hyperbolic PDEs. This is like a continuum, infinitely many feedback loops that can have a high gain. So this can very much go unstable, and it does in various application domains. So this was the first, I would say a breakthrough in which Jean-Michel Courant, Georges Bastin, and my student Rafael Vasquez participated. And one has to go to higher order norms in space, not just L2, not even H1, but all the way to the Sobolev norm H2 to achieve stabilization under these kind of nonlinear perturbations that are not only nonlinear, but include the perturbations involving the differential operator. After you design a controller for two coupled systems, what do? Well, you ask yourself, can I do it for more systems that are coupled, and are there applications for that? So the answer is yes. We were drawn to that. We developed that with for coupled systems of N and M counterconvecting PDEs, with a key where I want to emphasize that only one of the two PDE subsystems has a control input. That's the interesting part, that you have coupled PDEs of which you get to control only one or only M directly, and you have to control the remaining N indirectly to decouple them in a particular way. So this was an effort of several years, and ended up in various results. But maybe the more interesting is, what are the applications? Well, originally the applications that drove coupled hyperbolic PDEs came from various researchers in France who were working on the so-called Saint-Venant partial differential equations modeling shallow water waves, such as those appearing in water canals all over Belgium, France, and so on. This was the motivating first set of applications, but then it all got extended to oil drilling, where by oil drilling I mean both the instabilities in the structural oscillations of the drill string and the instabilities in the flow of the oil, natural gas, water, mud, multi-phase flows that tend to be unstable, tend to develop into plug-like instabilities that damage the equipment. Another set of applications is in laser chambers, where you can have thermoacoustic oscillations, just as in combustion chambers. I'm sorry to forget to list combustion here. That's so natural in me that's almost obvious. And road traffic, that'll say something about a bit more shortly. So not listed in this set of applications is one application that I would like to showcase, because it's simple, because maybe there is an occasional mechanical engineer in this audience, and this one is really, really clean and elegant. This is the so-called Timoshenko beam. Almost all of the PDE control theory sooner or later gets tested on the so-called Euler beam. But the Timoshenko beam is the most complex of the four beam models, and it doesn't even look like a beam. It is actually a system of two coupled, interconnected in both directions, wave equations. And this could be almost a whole seminar. I'll have to leave it at that, just saying that this is two coupled wave equations with different wave speeds and with the control only at one end. This is done by converting each of the two wave equations into two first-order hyperbolic PDEs, and then for those four resulting PDEs, designing a backstepping controller. What's the motivation? For example, the attenuation of these oscillations in the cantilever beams in the atomic force microscopy. All right, so after first-order hyperbolic PDEs, one realizes that one has in the process dealt with delay-like effects. And one asked themselves, well, what about systems with delays? I mean, we're engineers. Delays are one of the things that worries us the most and that we need to compensate. Right around that time, a couple of friends were doing some very interesting things with delay compensation. Anu here at MIT with the so-called Posicast adaptive control, and Merjan Jankovic at Ford for reasons that have to do with the automotive dynamics and the effect of humans in the loop. And I said, wait a second, you know, this special case might be more exciting than all of the general PD stuff that I'm doing. So I turned my attention to that and put a lot of effort into this. This was single-authored work, progressing from linear ODEs with an arbitrarily large delay D that needs to be compensated to nonlinear ODEs with a arbitrarily large delay. I can't say. I have to limit what I want to say. This is an exciting topic in which the so-called predictor operator needs to be developed, but let me leave that out. After that effort, I came across several applications. Some in congested traffic in communication networks, some in screw extruders for additive manufacturing or 3D printing, in which the delay is present and it's large, but it's not constant. It depends on the state, and you don't know upfront what the state is. So we focused on compensating non-constant delays in nonlinear systems as given here. This was the dissertation effort of my student Nikos Bekaris-Liberis. So having observed that delays of arbitrary length at the input or the output of an ODE could be compensated, the natural next question is in research is, I mean, if you can compensate a delay, which is the simplest of PDEs, can you compensate less simple among the PDEs at the input of an ODE system? So I put an effort into compensating parabolic PDE equations at the inputs of ODEs, or higher order hyperbolic PDEs at the inputs of ODEs, or cascades of hyperbolic and parabolic PDEs. So this was an interesting body of literature that developed before I even knew applications for it, and applications turned up within a few years for each and every one of these things. It's almost a rule that if the theory is interesting, an application is just a matter of a conversation with somebody who's worked on it before and knows the model. All right, so I'm now progressing towards adaptive control, and I want to say that the adaptive control was the motivation for developing PD backstepping, and was finally realized for all classes of PDEs. For parabolic, in which the reaction coefficient and this kernel F are completely unknown functions of space. For hyperbolic, where the coupling between the unstable first-order hyperbolic PDEs are unknown functions of space. And for systems with delays, where the delay to be compensated is not just long, but it's unknown. And it can be both underestimated or overestimated. So this was a lot of work, years of work, which I just show with a few slides. So it's clear how this history has marched. Let me now show two slides on applications that have taken more effort and consumed more time. The first of them is parabolic. It's in additive manufacturing. So they the phase change in materials between liquid and solid was modeled for the first time in the late 1800s by a physicist, Joseph Stefan, or Joseph Stefan as he's also known. This model is a very interesting model where the dynamics in one phase, in each of the phases, liquid or solid, are governed simply by the heat equation, with a boundary temperature set to the melting temperature between liquid and solid. But the interface is governed by an interesting ODE. The interface is a scalar spatial position quantity, and is governed by a nonlinear ODE. And what's interesting is that this nonlinearity is not given up front. It's the heat flux, which comes as a solution of the heat equation with this boundary condition, but it is a nonlinearity. So this was an effort that was driven by additive manufacturing. In the end, it was applicable to lithium-ion batteries. It was applicable to estimating the temperature distribution in sea ice, in large blocks of sea ice where you cannot access the internal temperature, and you want to predict actually the melting rates and how the things are doing. But I want to point out in LIDS that this model of phase change is also a model of certain social dynamics. Think of the phase change, the phase as an opinion on something, and one group of people holding a very different opinion from another group of people, and this phase change occurring somewhere in the space, in the age space, in the income, in the educational level space, and this needing to be either estimated, though not measured internally, or controlled and regulated to a desired set point. The other application that consumed considerable effort and gave good results was stabilizing stop-and-go instabilities in traffic flows. We don't need much introduction to that subject. I'm pretty sure that Boston is no better than San Diego or LA in that regard. And that subject, that phenomenon, is modeled by two PDEs, one for the density, the other one for the velocity. And where are we? We are in here. Our behavior, our driving style is captured in this term, which involves the set point that we our comfort level with regards to the distance to the driver in front of us, and this pressure term, which it takes a bit more to explain. So this problem was solved and only solvable with boundary control using backstepping. A number of other applications came up along the way. So I mentioned already water canals, oil drilling, and lithium-ion oil drilling is relevant because backstepping was used actually in experiments by the Norwegian company Statoil in several kilometer-long pipelines to estimate the downhole pressure. It was also used in a project with ARPA-E on lithium-ion batteries maybe 10 years ago in partnership with a Robert Bosch outpost, the U.S. Institute of the Robert Bosch company. So there have been some applications of PD backstepping that may be quite non-obvious. In vehicle swarming, the limit of having many vehicles is a PD. Once one goes to that limit, things get easier. They become more elegant. The clutter of a complicated graph cleans up and you get a PD. And if you have a leader, that's your boundary input. And that leader can perform stabilization and can perform also deployment. The instability of the swarm is something typical of this effort. Typically, you will see swarms that are stable. If left alone, they will be they will be stable. But you don't get interesting and complex deployment shapes with stable agents. You get interesting shapes when you have agents that don't want to be near neighbors. They want to run away from everybody, and you sort of rein them in with boundary control, and these figures speak for themselves as deployment figures in 3D. Extremum seeking is a topic I could have chosen because it's so interesting, you know, so worthwhile to talk about something that's gone on to result in, you know, thousands of patents and industrial applications. But I just want to say that PDE backstepping has had a role in extending extremum seeking to systems that have not ODEs, but have PDEs that need to be compensated, and that's the work with Tiago Ru Oliveira. Let me now get to the merger of PDE backstepping with machine learning. So, today, I don't think that a meeting that I had a conversation that did not involve machine learning. And everybody has a different role. Everybody's learning a different thing. So I have to tell you, what is my thing? What am I learning here? So one thing that after you spend decades in a field as a theorist, one thing you don't want to do when machine learning comes along as a disruptor of your area, one thing I don't want to do is walk away from everything, is just start from scratch and just forget about this complicated stuff that relatively few people can understand and redo it so that everybody can. So I found a role for machine learning in supporting the model-based designs. In other words, there are a whole bunch of model-based designs that I've shown you, and they are essentially transformations. They're mappings from models into feedback laws. So that mapping is something I want to learn and automate. Before starting to work on this, I did not even fully comprehend the complexity of these mappings. I've just been producing them, and it was only when I started thinking about machine learning that I started thinking about their internal structure and complexity. So for instance, I started with a reaction diffusion equation where the reaction coefficient is a function of space lambda of x. My control design is a mapping from the reaction coefficient into the gain function, gain kernel k, a lowercase k, and I denote this mapping with the calligraphy k. This is a nonlinear operator from an one-dimensional domain, an interval from 0 to 1, to a triangular domain for the gain kernel. Well, that is what I want to learn and approximate, and you will see why. I've been computing these gains, lowercase k, for a given lambda for 2 decades. But then I asked myself, what is the mapping so that I don't have to compute it next time, but I just plug it into a formula which is a neural network approximation of that mapping. In other words, find the mapping once and for all, and you will see why once and for all matters. So before I show those details, let me make sure I don't run out of time to acknowledge the collaborators. So the moment an interesting new idea comes up for a topic that has a 20-plus year history, the possibilities are enormous. And there is so much to do for so many people so instantly within 6 months, 8 months. These and now other people have joined in these efforts, some really incredible talent among them. I will not single out anybody individually. So let me now move on to illustrate what I'm talking about. So these last 10 or so minutes these last 10 minutes give enough time to show one example. So I will not be going to the most general of those designs that I've shown you to show you how we do that. I'll go to the simplest one among them. There isn't a simpler example imaginable worth presenting pedagogically to introduce this notion. The more complex things have already been, there is considerable development on more complex systems. But this is the benchmark, a system that is notationally simple, but conceptually definitely not trivial. So this is a transport PDE with a recirculation. Any chemical engineer in the room will not need much elaboration on this. But recirculation can occur in more than just chemical reactors. That there can be feedback being applied even from routing apps to the drivers and influencing the behavior of drivers along the entire freeway. So you see how the outlet of this PDE is being fed back everywhere within the domain with this gain beta of x, which I highlight in red because it represents danger. This is the destabilizing feedback from the recirculation. And if the words do not suffice, I show you here what I mean by destabilizing. There are these oscillations which grow as time progresses if you don't apply any control at the boundary that can be actuated. The boundary to be actuated is x equals 1. Okay, so let me now step from the motivation to the methodology. I'm going to step back to something incredibly familiar and arising in a surprising manner in this domain. And this is the sensitivity and the complementary sensitivity functions from our basic undergraduate or graduate level robust control courses. When I say sensitivity and complementary sensitivity, I mean exactly those that you know under those names, and you know that their sum is the identity operator. It won't be long until we hit the centennial of Bode's work on these functions and the performance limitations. But I want to talk about not the sensitivity functions, but the sensitivity operators. Not the Laplace transform of the impulse response, but the operator from the impulse response of the open loop system into the impulse response of the closed loop system. So the sensitivity operator is this mapping from the function beta into what you see as the inverse Laplace transform of 1 over 1 minus the Laplace transform beta. I use the positive feedback convention for reasons that offer some convenience in notation. And likewise, the complementary sensitivity operator is the identity minus the sensitivity operator, and it's given by this, most famous of our formulas. The Laplace transform divided by the Laplace transform plus by 1 plus the Laplace transform. I don't think this question has ever been asked because it wasn't necessary to ask it in the context of linear control, to my knowledge. But in the context of what I use it for, it needs to be answered. And that question is, are these continuous operators? And I answer with this. This is a theorem, something that needs to be proven. I don't put any label on it. I establish that these are not just continuous operators, but they are Lipschitz operators. It's good to actually have a uniform Lipschitz constant. These Lipschitz constants are valid for all input functions that are L infinity bounded by the constant capital B, and which are themselves Lipschitz functions of their argument, and their argument is x. So it's potentially confusing. I'm talking about the Lipschitzness of an operator and imposing a condition of a Lipschitzness of the input to the operator, two totally different Lipschitzness concepts. So these are the Lipschitz constants for the sensitivity and the complementary sensitivity operator. One more thing I want to show you follows from the recent work in neural operators, an area in which there are many authors, but I'm employing a theorem of one particular group of authors, Karniadakis at Brown University and his authors, for the so-called DeepONet form of a neural network, which says the following. So there's a theoretical result. It takes tens of pages to prove, unfortunately, and it's an existence result. It says that the actual operator, capital K, can be approximated arbitrarily closely with a neural network to an arbitrarily small error, epsilon. And that's it. This is the result. Provided that the input space is compact, and the compactness is ensured by assuming that the inputs are Lipschitz themselves and bounded by B. I know that somebody will ask me sooner or later, you know, that's an existence result, but how big is the neural network? What kind of neural network, and so on. This is not my area of specialty, and this topic is progressing rapidly. Whatever I say now might be an obsolete answer in a few months. What I can tell you, though, is that these being existent results, they are conservative. For example, I know that a sufficient condition for the number of nodes in a neural network for a PDE whose recirculation coefficient is bounded by capital B is on the order of B to the power B. Now, if that B is 20, that's an enormous number. It's a sufficient condition. But there is now also a necessary condition. The necessary condition is roughly that you need at least e to the power b nodes. So this is the truth about approximation theory. It has nothing to do, nothing to do with control or stabilization. There is a price to pay for approximating functions that can peak very high. That's essentially this. So let me now come back to this PDE. So that is the PDE, and the control of that PDE progresses using PDE backstepping. I've shown you the PDE backstepping transformation as the difference between the identity operator and a certain Volterra operator of the second kind. But I'm now showing you that for this particular example, this backstepping transformation is actually the convolution of the sensitivity operator acting on beta with a state. Very interesting. And the control law is the convolution of the complementary sensitivity operator acting on the recirculation function with the measured state. In the target system, the recirculation is wiped out by these two ingredients, namely the backstepping transformation and the feedback law. So now I want to get to the key part of this, which I probably did not emphasize very much back in February. And that is the simultaneous offline and online learning taking the form of adaptive control for PDEs with unknown functional coefficients. If you may recall that I was showing you a certain PDE of a second order for the gain kernel labeled by lowercase k, and that PDE can be converted into an integral equation whose state is capital G, and so on. So there are some complicated PDEs to solve, which you cannot solve at every time instant as you estimate the parameter in real time. So this is where the machine learning will be crucial in enabling adaptive control. So let's suppose that this beta, for which, if known, I could always design a controller, is actually an unknown function. And let me denote the estimate of that unknown function of x as beta hat. This now becomes also a function of time because it's estimated adaptively in real time. How would you estimate it? Let me first get this out of the way. How do you estimate this unknown function of space? There are several approaches, and Anu knows this. There's a whole forest of system identification methods, even in continuous time, or I would say especially in continuous time. It's nice and elegant and pretty. And one of them takes this form. It's a Lyapunov-based gradient-like update law in which Anu for sure, and hopefully others, recognize the familiar ingredients. Something that's called a regressor, something that's called a regulation error, and something that's called a normalization. Exactly the details don't matter. I need 10 to 15 minutes to get into those details. But the structure is familiar. This object, what is it? It's not a PDE because there are no partial derivatives of beta hat. There's only a time derivative. There are no spatial derivatives, but there are integrals in space. So it's a nonlinear, infinite dimensional, ordinary differential equation. All right. I will show you how this works. Let's get the theorem out of the way. The one theorem I want to show you is this one because it's such an effort to prove it. So the theorem in the most stripped down form, there are some assumptions. Certain things need to be small enough in the design. The gain cannot be too high, blah, blah, blah. I want the key thing to be clear. The main result is that this system is Lyapunov stable in the sense of there existing a class K infinity bound on the norm of the entire plant state and the parameter estimation state expressed in terms of a bound that contain the initial value of that norm. So this is how you want to claim stability in adaptive control every time, and in particular when you're dealing with a PD. And in addition, what you really want as an engineer is not just stability. You don't want just a bound. You want to regulate something to a set point. In addition, set point regulation in L infinity norm, namely pointwise in space, is achieved. Let me show you some simulations, and then I'll come back to close with a few remarks on the proof of this theorem. So here's how this works. In open loop, the system is unstable, and you've seen already one version of this oscillating growth of the system state. When an adaptive controller is applied, you see this transient in which what's bad in open loop begins to emerge and is then suppressed. Anu is smiling because I hope she credits me for being honest, showing you the ugly truth that you cannot learn things without getting in trouble first. So I let the system get in trouble a little bit, so here's what happens at the same time with the parameter estimate. The parameter estimate is learning. And once it has learned a good enough parameter, functional estimate, the controller immediately says, okay, things are now working, and suppresses the instability. And the moment the instability is suppressed, the information, the trouble is gone, the learning is over, and the parameter estimate is never learned perfectly. And that's fine. So no assumptions of persistency of excitation, but regulation to zero through a several-step process of sort of incipient instability, learning, then stabilization, and then complacency of the update law because has no reason to learn anymore. The proof, this is what I'm proud of. No, I mean, simulations are great, but they take 1/100th of what the proof takes in terms of time. So the proof is complicated because there are three types of perturbations in adaptive control of this kind. One comes from the fact that the PD for the kernel is not being solved online exactly, but it is approximated with this machine learning object, with a neural operator. So there's that approximation error. There's also the parameter estimation error, which is killed by the update law. And finally, there's an error coming from the time derivative of the output of the neural operator, which is being fed by the parameter estimate beta hat. So let me summarize. The ability to replace solving the PD at each time step for each new estimate by a neural operator, which is trained offline in a matter of minutes. I mean, minutes are a long time with today's technology. On laptops with GPUs, this offline training takes minutes. On older laptops, it takes hours. Okay. So this speed up, this elimination of the numerical solution at each time step, speeds up the implementation about 3 orders of magnitude, and that is what makes a difference between adaptive control for PDs being just a notion, which it was until a couple of years ago, and being implementable. Well, with that, I thank you for your attention, and perhaps we can take a question.